Good morning. Gonna wait for a few more people. We'll wait one more minute. Hello. Okay. All right. Welcome back, everybody. I hope you had a nice, restful vacation. Um, Mine was really nice. I always know I had a good vacation when I can barely remember my passwords when I get back. Like my work email login and all that stuff. It's like, that was a good vacation. Um, so we have a shortened class today. Today's class goes from... Oh, you know what? Class hasn't even started yet. Class starts at 9:10. I was confusing myself. So I guess I'll wait a little bit longer. Oh, man. Did anyone get to see the great opposition between Jupiter and Saturn? It was pretty cool. Could see both of them in the same... They were really close to each other. You could see both of them through the telescope at the same time. Yeah. All right. So just to remind you guys, this is a shortened class today. So this class is going to go from 9:10 to 9:40. And furthermore, your period 4 is going to start at 9:45. So you only have a 5-minute passing period. So because of the time constraints for this lesson, we are not going to have Zoom room. We will have office hours as usual if you need to come by. All right. So, don't forget to submit your attendance form. All right. So the attendance form is still active today, and I will use that to take attendance. And that will be the only thing that will be used to take attendance today because there is no Zoom room. So I have no idea who's watching. All right, so let's go ahead and get started. So what we're going to talk about today is musical instruments. Okay, musical instruments. And in particular, so this is going to be over the next 2 days, we'll talk about musical instruments. But in particular, today we are going to talk about stringed instruments. Okay. So when I say a stringed instrument, all right, I'm going to draw that. Well, some examples of stringed instruments are, violins, cellos, guitars, pianos have strings. Okay, so they can have multiple strings, but we are only going to focus in on one string. Okay, and we're going to see if we can predict the frequency that string is going to play. Okay, so I'm going to draw a string like this. So these are the two ends. So for example, if you have a guitar, okay, this would be the neck of the guitar, and this is the other part of the guitar where the string is attached. And then we have the string goes between those 2 points. Okay, so this is the string in its equilibrium position. Okay, so the string is just, it's not moving, it's just completely straight. Okay, we're going to call the distance between these 2 points L. Okay. Now, if we think about the string, when it's vibrating, so maybe if you were to take a snapshot of the string vibrating, maybe it looks like this. Oop, why is that so dark? So maybe it looks like this. This is the string vibrating. One thing you know for sure is that as the string is vibrating, this end is fixed. Okay, because it's literally attached. Okay, and this end is also fixed. So both of those ends are fixed because the instrument is sort of like, the string is pinned down at each end. Okay. So what that means is that there are only certain ways that the string can vibrate. Okay. So I'm going to draw some of those ways that the string can vibrate. All right. So one of the ways is it can have a single hump. So the string is kind of going like boing, 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 like that. Okay. So the string looks like this for half the time, and it looks like this for the other half of the time. Okay? And then, so here's the equilibrium spot is in the middle. So the string is vibrating boing, 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 like that. Okay? And so we can see that in the middle of the string, right here, the string is really swinging up and down. So that spot where the string is really going up and down is called an antinode. Antinode. Okay? It's a place where the displacement of the string is huge. Okay? Then if we look at each end of the string, the ends of the string are not moving at all because they're stuck, they're pinned in place. So these are called nodes. So this, if the string is vibrating in this way, it has two nodes, one at each end, and one antinode in the middle. Okay? And so the string is going like this. All right? So there's another way that the string can vibrate. And that's a vibration where the string is going kind of like this. Oh, I don't have my slinky with me. All my slinkies are in the classroom, or else I would show you. But it will vibrate. Maybe we'll watch a video in the next class of the strings vibrating just so you understand. So if you were to take a snapshot of the string at one instant, it would look like this. And then the other half of the time, it will flip and it'll look like that. So if we look at the instrument when it's like this, how many nodes do you guys count? How many spots are there where the string is staying in its equilibrium position? And how many antinodes do we have? So there's a different number of nodes and antinodes from this type of vibration. So yeah, there are three nodes. So there's a node here. Now there's a node in the middle, and then here's a node. And then how many antinodes do we have? Two for the antinodes, okay? So this would be an antinode, and this would be an antinode. All right? Whenever I'm drawing these pictures, I always think of the Beatles song, Hey Jude. Na, 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 na. Okay. So if we think about this picture that I've drawn here, to me this picture looks like a football. Okay. This picture looks like two footballs end to end. So the next type of vibration that a string can have, okay, is going to have three footballs. Like that. Okay. So that's a wave. All right. So you can see that each time we go to the next possible way that a string can vibrate, we squeeze in another football. Okay. So I'm going to squeeze in another football. All right. So the next way that the string can vibrate looks like this. I'll draw one more. That. Boom. Okay. So these different ways that the string can vibrate, and so we get to the next way by squeezing in another football into the vibration pattern. These are called harmonics. Okay, harmonics. This is the first harmonic. This is the second harmonic. This is the third harmonic. This is the fourth. This is the fifth. And there are basically, there's not an infinite, but there's basically an infinite number of harmonics. A very, very large number of harmonics. And the harmonic number is just telling you how many footballs are there in the vibration pattern. Okay? Now, if we look at this drawing I made of a string that's actually vibrating, you can see that this picture doesn't look like any of these pictures. But it turns out that this picture is actually a superposition. So remember, a superposition is when you take waves and you combine them. It's a superposition of all of these harmonics, and you can make it look like that. Okay? So an arbitrary way that a guitar string can vibrate is always a superposition of its harmonics. Okay? So yeah. So let's see if we can't figure out what is the wavelength of each harmonic. Okay? What is the wavelength of each harmonic? Well, we can see a wave, a full wave, has a peak and a valley. Okay? So the wavelength, so if we look at, for example, the second harmonic, okay, it has one peak and one valley. So that's a full wave right there. It has a peak and a valley. So the wavelength of the second harmonic is going to be the full length of the instrument. So the wavelength of the second harmonic is L. Okay. If we look at the wavelength of the first harmonic, okay, if you look at the wavelength of the first harmonic, we can see that it only has a peak, or it only has a valley, but it doesn't have a peak and a valley simultaneously. So what do we have to multiply the length by to get a full wave? Well, a full wave would also have a valley, so I would have to extend the instrument to twice as long in order to add the valley in. See, the valley goes out over here. Okay? So a full wave is actually twice the length of the string. Okay? If we look at the third harmonic, okay, here's a peak and here's a valley. So that means that this distance right here is a full wavelength. Now each football is the same size. I kind of messed up in my drawing, but each football is the same size. So so that means because we've divided this space into 3 footballs, a full wavelength is 2/3 of this entire length. Okay? So this is 2L over 3. 2/3 of the entire length. If I look at this one, a full wave is that distance right there, because that's a peak and a trough, a crest and a trough. And I can see every football being the same length. I've divided the region into um, 4 footballs. So this is half the length of the string. So the wavelength of the 4th harmonic is L over 2. Okay. Here I can see that a full wave is this. That's a full wave because it has a peak and a valley. Okay. And so it has a peak and a valley, and that is 40% of the way across the string, which can also be written as 2/5. So the wavelength of the 5th harmonic is 2/5 L. All right. Now I'm going to write some of these in a more suggestive fashion to see if you guys can catch the pattern. So I can write 2L as 2L over 1. All right. I can write L as 2L over 2. Lambda 3 is 2L over 3. I can write L over 2 as 2L over 4. This is 2L over 5. So based on this, who can tell me what is the pattern? What is the wavelength of the nth harmonic? Who can tell me the pattern? Two L over N, excellent. So the pattern is 2L over N. This is the wavelength of the nth harmonic. Okay? Based on this, we can find the frequency of the nth harmonic. Okay? Okay. So to find frequency, we're going to use that equation that we learned before the vacation, which was V equals lambda F. So this relates the wave speed to the wavelength and the frequency. And I can see that the frequency is, okay, the frequency is V over lambda. Okay, so if I invert the wavelength, I don't have 2L over N, I have N over 2L. Okay, so I have frequency times N over 2L. Okay, so I'm going to write it as NV over 2L. That is the frequency of the nth harmonic. So, so these are our two equations for today, and then we're going to spend the last 10 minutes of class just kind of talking about the implications. Now, your assignment for this week, you can't do it after today's lesson. Okay, so after Thursday's lesson, you will be able to do that assignment. All right. So don't attempt it yet. So now we're going to try to interpret this. When you pluck a string, you create a superposition You know what? Give me a second. just remembered I have the ukulele. Okay, so, oh, it's already in tune. Okay. Have not played ukulele in a long time. I thought I wanted to learn it, but then I just got bored with it almost immediately. I like piano much more. So anyways, I pluck a string. I am creating a superposition of all the harmonics. Okay? But if you think about it, so a superposition of all the harmonics, but there's one frequency that you hear sort of above all the other harmonics. Because remember, in music, a note in music is a specific frequency of a sound wave, okay? You hear, you perceive the note as being the first harmonic. Okay? The additional harmonics give the sound its timbre. Timbre is another word for the quality of the sound. So, you know, if I can play the same note, I can play the same note on different instruments, and you might be able to tell that when I played the note on this instrument, it's a ukulele. When I played on another instrument, it's a piano, or it's a violin, or whatever. So the thing that gives the instrument its unique sound, its fingerprint, if you will, is the higher harmonics. Okay? Different instruments have different amounts of the higher harmonics that give it a unique sound that's particular to that instrument. Okay? But the one that you hear is the first harmonic. All right? Now here's another thing. What if I'm playing the ukulele, okay, and I want to make higher notes? What I should do so you can see that what I'm doing to make a higher note is I'm making the vibrating portion of the string shorter. Okay? So what that means is we are reducing L. Okay? So we can see that as the length of the vibrating part of the string goes down, so as the length goes down, the frequency goes up. Okay? So this is exactly, so this equation expresses what we are seeing here. Okay? The note goes up as the vibrating portion of the string gets shorter. Okay? So that's really cool. All right? Now, what is different about different strings? Different strings, because there are 4 strings on a ukulele, there's 6 on a guitar, there's I think 249 on a piano. I'm not sure exactly. Does anyone know how many strings are in a piano? Because I think each note has 3 strings, at least for the higher pitch notes. I'm not sure how many strings in total. There's 88 keys in a piano. Oh, so that would be 264. Maybe there's 264 strings. I'm not sure. Different strings. Now, if we look at all these different strings and I pluck them, all these strings have the same length, right? Because I'm not holding them at different spots. Okay, but they all sound different. That's because these strings have different thicknesses and different tensions. Okay, and what that means is that the wave speed is different along each string. Okay, so different strings have different wave speeds, which is why they sound different. Okay. Okay, so 230 strings in a piano. So that must mean that the bass notes, I think, only have, some of the bass notes might only have one string. Okay. And the other thing I wanted to talk about is tuning. Okay. So when you are tuning a string, okay, when you are tuning the string, you're adjusting this knob right here, and that is changing the tension in the string. Now, more tension, so tuning, more tension in the string raises the wave speed. And if the wave speed goes up, then the frequency of the string goes up. Okay? So so you can adjust the frequency by changing the tension. So that's how you tune a stringed instrument. One last thought. Stringed instruments actually will, their frequency will go up in cold weather. So let's see if we can explain why that is. If you take a stringed instrument into cold weather, the strings, most things when they get cold, they kind of contract and shrivel up. So what happens is the string gets cold and it shrinks a little bit. But it can't shrink because it is held at both ends. So what happens is, because the string is trying to shrink in the cold weather, the tension in the string goes up. Because the tension goes up, the wave speed goes up, which means that the frequency is going to go up. So in musical language, if you take an instrument into a stringed instrument, we'll talk about wind instruments next time, but if you take a stringed instrument into cold weather, it will go sharp. All right? So that's my lesson for today. I hope you enjoyed it, and I will see you on Thursday. Make sure to submit a